Section 6, we have oxidation-reduction reactions, or what we will frequently call redox reactions. I know when we do redox, we flip the order of those. There's nothing wrong with calling it reduction oxidation. It's just not the normal, but let's dive right in. This one starts with a whole bunch of examples. Yes, it occurs in all those places. It occurs in some other places. That arrow is really out of place. It belongs down here, but we're just going to jump into what they actually are. I apologize that is almost off the screen there, but in a redox reaction, you have a transfer of electrons during the reaction. Now, I will say that these A's and B's are not the same as they were previously. In a redox reaction, we normally have something that goes from not having a charge to when it loses that electron having a charge. And we have another piece that does the opposite. It starts out with a charge and then ends up with not a charge. And so then the piece that loses electrons, that is oxidation, and the piece that gains the electrons is reduction. Oil rig is a great mnemonic for using it. It is simply that oxidation is loss of electrons and reduction is gain of electrons. I learned another mnemonic, and it's one that you might hear me use as we go throughout here, but Leo says GR. And this is loss of electrons is oxidation, and gain of electrons is reduction. So the says doesn't stand for anything. Either one works as a mnemonic to memorize them. There are others out there, but these are the most common ones, and they are worth memorizing to help you. I will point out that you get a redox reaction. You're pretty much guaranteed to have a redox reaction if you have a single replacement reaction that involves a metal or ionic compounds. It is less common in covalent because covalent, they share the electrons, so there's not an actual gain or loss of electrons. It's also going to happen in many of the synthesis reactions and decomposition reactions, especially if there are ionic compounds in there again, because the ionic involves charges, and these transfer of electrons is going to result in charges. I wish they did this one a little bit differently and introduced it a little bit differently. Personally, I would start with the reaction here. So here we have a synthesis reaction. And we start out with copper that does not have a charge. It's got no charge, and oxygen that does not have a charge. And we end up with copper oxide. Well, copper oxide also doesn't have a charge. And so you're looking at that and you're saying, wait a second, if they all don't have charges, how is this a redox reaction? Well, it turns out that when we have them bonded together, it's because there's been a transfer of electrons, which is what we're getting ready to get into with these above things. But the transfer of electrons includes the fact that copper in copper oxide is going to have a charge. It's going to be a 2+ charge. And oxygen, when it is ionic, it's going to have a 2- charge. And so what has happened is copper has sent electrons to oxygen. And so because it has lost electrons to oxygen, then copper has had a loss of electrons. And a loss is oxidation. The oxygen, on the other hand, has gained those electrons. It went from no charge to negative charge, and because electrons have a negative charge, it has gained those electrons. And so a gain of electrons is reduction. Now, I'm going to clear all of this and explain what they meant up here. And first off, and in addition to that, I did a quick cut there because I noticed that the things were all shifted off. The arrow should have been here for our yields, but what they've done up here are what are called half reactions then. And what happens is each piece here goes through a change. So you end up with copper, and copper goes from being a copper with no charge to a copper with a 2+ charge, so it had to gain 2 electrons. Well, because it's going to take 2 coppers to react with the oxygen down here, we have to do that twice. And so that's going to give us then the 4 electrons that we see here. Oxygen then, again, started out with no charge, and it gains those electrons. And so then oxygen here ends up with a 2- charge, and there's 2 of them, so that's the total of the 4 electrons. Then what we do is we view this as 2 equations that we can add together. So when we add those together, then we end up with 2 coppers from the 2 coppers there. We end up with 1 oxygen from the 1 oxygen there. We end up with our copper and oxide bonding together because we have a 2 plus and a 2 minus, and so then we end up with copper oxide there. And the electrons, they cancel out because on one side we have plus 4 electrons, on the other side we have plus 4 electrons. If you're doing algebra, when you rearrange that, you would subtract it from one side, and then you'd end up subtracting it from over here, and the two of them cancel out. And that has to be true, that the number of electrons lost is always equal to the number of electrons gained. Now, it's real clear here to see on the oxygen that it has gained the 4 electrons. And gain of electrons is reduction. And so the oxygen, we say, is reduced. It's a little bit harder to see that the copper has lost electrons because we put the electrons over here on the product side. But again, you could write it over here as minus 4 electrons. Either one works, and then it's really easy to see that this is a loss of electrons, and losing electrons is oxidation. And you'll notice I just mixed the two different mnemonics here, oil rig and Leo says Gur. Either one works, whatever works for you. And I will point out here that the Statue of Liberty was a copper statue. Unfortunately, we didn't have color photography at the time, so we don't have any photos of her being all copper. And it was known that this was happening. It wasn't like we were surprised that she oxidized or rusted. Rust is technically just iron oxidizing, but it is like rusting here. We knew this would happen because it's been happening since Greek times, probably beforehand, when original copper statues were made, and early bronze statues were made as well. And you always get this patina on the surface, is what that is called. Instead of being called rust, we call it a patina. But that patina, interestingly, actually serves to protect the lower layers. And so if we wanted to, we could scrape off the Statue of Liberty and expose the copper that's underneath. But it's really thin metal that was used to make her, and if we did that, it would just turn green again, and we'd be making her thinner and thinner and thinner each time. Eventually we'd wear through that really thin copper sheeting there. But unlike rust, where when iron rusts, you end up with these pores opening up in the iron oxide that allow oxygen to get the deeper layers of iron that then keep doing the same process. Copper and also aluminum, they end up forming a oxide that has a really tight crystalline pattern that prevents oxygen from getting further into and rusting again the lower layers of metal, the inner layers of metal, and so then it actually serves as a protective coating and prevents it from further oxidation, and so you don't get that same deterioration in terms of wearing out the metal. The aluminum oxide, it's so thin, it's only a few atoms, a few molecules thick, that it makes aluminum really oxide resistant. We don't even get a color change there with aluminum oxide, which is a white color otherwise. I will point out there's at least one famous painting where a painting was done of the Statue of Liberty before it was assembled. They actually took parts around on trains in America to try to raise funds to actually build the structure and to buy the island where she was going to be assembled. And that painting does have the Statue of Liberty in a copper color, and you can see some black and white photos of her disassembled as well back then. There's all sorts of other fascinating history we could get into with that, but this is chemistry, so we'll move right along. Here we have another example. We have zinc metal, and I'm going to write out the reaction equation up here. We have zinc metal, and we have copper sulfate solution. And it's going to react to form zinc sulfate and copper metal. And you can see here the coating of copper that exists on the surface of the zinc. And what is happening is copper ions are coming in here and replacing. It's a single replacement reaction. Copper ions are replacing the zinc, and they are leaving and gaining a charge through that transfer process. And so the zinc ends up in solution, and we end up forming zinc sulfate out here, which they don't label as the product, but it's there, you can see in the reaction, and you're left with then zinc ions in there. Well, one thing I'll point out, and it's something that we're not going to get into right now, but it's something called a net ionic equation. It turns out that we can write this as zinc plus copper plus sulfate. And for copper and sulfate, because they are bonded to one another, when they dissolve, they do break apart into individual pieces. It says here we have a solution of copper 2 plus and sulfate 2 minus ions, or just sulfate ions, because sulfate ions are always 2 minus, and they are broken apart in solution. So we can write them like that. On the other side, it turns out that the sulfate is also still in solution, that zinc sulfate is aqueous, and so then we can write it out as zinc, and because it's bonded now, it has a charge. The sulfate has a 2 minus charge, and then we have the copper metal there. Well, in this case, our zinc starts out with no charge. We don't have to write the no charge, but I like to put the charges on these when I'm doing a ionic equation. Because when you do an ionic equation, you have to have some charges in there, and to me it's just simpler to make sure everything has a charge so that I don't forget to put the charges on the individual pieces. It's very easy to do, and so I just put charges on everything, and that means putting zeros on there so I can make sure that yes, everything does have a charge. Well, it turns out that we can turn this into something called a net ionic equation because sulfate is there on both sides. It didn't do anything. It didn't change. Oh, it looks like I maybe accidentally wrote that as a plus. It's a minus. My apologies. I'm not going to go back and redo all that. And so because it cancels out, we can get rid of it. And we have that as our net ionic reaction equation. From here, then, we can see, and we could have seen it on the prior one, we don't have to go all the way to net ionic. We don't even have to go to ionic for it. We could do it based off of this reaction equation. I just think it's easier to see this way. But we could see here that zinc went from having a no charge to having a positive charge. Well, in that case, it has gone from having no charge to a positive charge. That means it must have lost electrons, and loss of electrons is oxidation. Copper has to have done the opposite. You always get redox reactions. You always have to have both halves occurring at the same time. You can't have one without having the other. So copper must have been reduced, but we can verify that here by looking at the change in charge. It went from positive, it gained negatively charged pieces, and in gaining negatively charged pieces, it is reduced. From there, what we can do then is write out what's called the half reaction. And so the half reaction are those reactions that included the electrons. So here we have zinc, and zinc becomes zinc 2 plus and 2 electrons. On the other side, we had copper that started out 2 plus, and it gained those 2 electrons to become copper with no charge. And copper and zinc there have no charge. And so here we can see there's a loss of electrons, and loss is oxidation, and so that's our oxidation half reaction, and gain, this is our reduction half reaction. Although you're not going to be asked to write half reactions, but instead be able to identify them, you can do it. They're not that bad to do, and I think it helps to have this in the background in your mind so that you know exactly what occurred. Anyway, over here we're asked to identify these as oxidation or reduction. So here tin has lost electrons, so that's oxidation. Iron here is gaining electrons, so that's reduction. Notice here in this particular case, it gained electrons and it still has a charge. We don't have to go all the way to neutral. We can just change the charge of something, and that is still a change in charge, so it still involves a gain or loss of electrons. In this particular case, it's a gain. And here on this one, this is also reduction. Yes, you could, for simplicity's sake, just memorize which side the electrons are on. You just have to be careful in case you ever see a reaction equation where instead, on this one, for example, it's Sn minus for electrons. It's not the standard way to write it, but you will see it sometimes. Then the electrons are on the left, but it happens to be a oxidation reaction. Normally, though, in your oxidation reactions, you are going to have electrons on the product side, and in your reduction reactions, you're going to have electrons on the reactant side. And reduction occurring on the reactant side, well, they both start with R. That alliterative way is not a bad way to remember it. Having said that, it's harder when you have a reaction like this where you don't have the individual half reactions, but instead have the whole reaction and have to identify the individual pieces. So what I can see here is that silver goes from having a positive charge to no charge. Well, to get rid of that positive, it would have had to have gained electrons. And so a gain of electrons is reduction. And so then the other one here must be our oxidation. And so there must have been a loss of electrons, and the loss is oxidation. And sure enough, this thing went from having a negative charge to being neutral, and so it had to get rid of those negatively charged pieces, that is the electrons. Now, to be clear, the reduction reaction forms this. For the question here, they say which reactant, that's going to be the left side of the reaction equation, is oxidized. It is the silver, and not just silver, but silver ion, or silver plus, silver 1 plus, silver 1 even, is what is oxidized. The reactant that is reduced is not chlorine alone, but the chloride ion with that charge there. And so they're asking about the reactant side on both of these and which reactant goes through each process. It does turn out that there are some reactions that go in reverse, and for reactions that go in reverse, if you were to do the reverse of this reaction, your oxidation reduction flip, because if we gained electrons to go from silver 1 plus to silver, then to go back to silver 1 plus, we would have to lose those electrons we gained. And so if you flip the reaction, you also flip the oxidation reduction. I will point out here specifically that silver compounds used to be used in photographs. A lot of your old black and white photographs are real sensitive to light. There is a process called fixation that kind of fixes them and is supposed to stop the reaction, but it's not perfect, and you still can get that change there. But that silver compound, we were relying on the film being sensitive to light to cause a color change, and then that color change is what actually developed our photographs. And so that is just an extra application for you, in addition to sunglasses that change colors. Your transitions lenses is the brand name there. That is a reaction going on within the lens itself, where we go from having compounds that are clear to compounds that are not as clear and start reducing the amount of light you see. This one here is a phenomenal application that occurs in your body as part of the ATP process, or specifically something in the citric acid cycle, as your body is going through its metabolism processes. And if you take 111 with me, we'll get into this specifically. You're not going to need to know it for here, so I'm going to just move right along. Here we have another example of why methanol is toxic, a wood alcohol. If you take 111 with me, I have a funny story that goes with that. But what ends up happening is your body can't digest that the same way that it can ethanol. And for those of you who are CCP and high schoolers, you shouldn't be consuming the alcohol right now anyway. Heck, many of you in early college, you're not old enough yet. Please don't drink. And if you do, shame on you, but please drink responsibly, please. Anyway, ethanol is what your body can process. Your body will try to process methanol, but it can't, and it ends up through a series of redox reactions forming formaldehyde. Formaldehyde is stuff that makes dissections stink, because that's the preservative we use in them, which then goes on to form formic acid, which itself is toxic, which then also goes on to produce byproducts. If your body produces too much of these in the middle, though, before it can completely break down those, it can be toxic. It can result in blindness, or more often death from this. And it's something that occurred a lot in the prohibitions. People tried to make their own alcohol and did it unsuccessfully. It's also something our government did to kind of punish people who chose to break the law. They put out a whole bunch of methyl alcohol out there for people to consume. A couple other characteristics before we wrap up here. Oxidation does always involve a loss of electrons. Reduction does always involve a gain of electrons. However, we can also see them as adding oxygen or removing hydrogen for oxidation. Or we could see it as removing oxygen and adding hydrogen. That is the opposite. Oxidation and reduction are opposites for some reactions. And of course, not every reaction has oxygen and hydrogen, but many of our biological reactions have those. And again, if you take 111, we see these two way more often than we see the first ones, even though the first ones always occur. As a side note, if we're adding in oxygens or removing hydrogens, we are going through a loss, or vice versa, a gain of electrons. That is occurring within these, but sometimes it's just quicker and easier to identify the reaction based off of these changes of oxygen and hydrogen than it is to try to figure out which one's gaining and losing electrons. Anyway, that finishes section 6.